We've gotten pretty far into this concept of the derivative. Now we're going to start looking a little bit more at the idea of the extrema, in other words, the maximums and minimums of a graph, and how they relate to the derivative of the function. So we're going to start with this function, f of x equals x plus 4 over x squared. And I'm giving you the graph. If you don't believe that that's what the graph looks like, then go ahead and punch it into your favorite graphing calculator and see that that's what it looks like in quadrant 1, at least. And then consider that I'm asking about the point 2, 3. It sure does look like 2, 3 is the minimum. If you take it at face value that I'm telling the truth, that the derivative, that the point 2, 3 is in fact a minimum of this graph, just based on the looks of it, then my question would be, what does the derivative of that function equal? Now, we know enough about the derivative to know that it probably equals 0, based on the fact that it looks like the tangent line of this graph is horizontal at the point 2, 3. But what I would like to do is actually analytically verify that it is equal to 0, that the derivative does in fact equal 0 at the point 2, 3. So let's take a look. We're going to see if we can figure out what the derivative is. So first of all, I might rewrite this as x plus 4 times x to the negative 2. That gets us ready to take the derivative. And then when we differentiate, we get 1 plus negative 8 times x to the negative 3. And if we're going to try to find the derivative at this value, at this point 2, 3, then we're going to have to evaluate f prime of whatever the x value is at that point, namely 2. F prime of 2 equals 1 plus negative 8 times 2 raised to the negative 3. Well, we know that when you raise something to the negative power, it means you're going to drop it down to the denominator. So 2 raised to the negative 3 is the same thing as 1 over 2 raised to the positive 3. So then we get 1 plus negative 8 over 8. But wait a second, we know that negative 8 over 8 is negative 1, and 1 plus negative 1 equals 0. This is not surprising. We already kind of figured that the derivative was going to equal 0 there, just based on the looks. All right, so that's one possible way to have a minimum of a function. Now let's take a look at this graph here. Again, this is a graph that you may not know what it looks like just based on looking at the equation, but if I also give you the graph, then it should be fairly evident that the point negative 1, 0 is a maximum on this graph. It's the highest point in that particular area, at least. So the question becomes now, what is the derivative at this point? Again, we already know enough about derivatives to figure out what the value of the derivative is at this point. You should be saying, oh, sure, it's undefined because there's a sharp turn. We might call this a cusp. We might call it a sharp turn, whatever you want to call it. I'm not really too concerned about that. It's not a nice smooth curve. This function is not differentiable. It comes up and it hits that point and it abruptly changes directions. So we kind of expect this derivative to be undefined. Let's go ahead again and verify it analytically. We'll take a look at g prime of x to find the derivative at that point, and we'll take the derivative of this using the power rule, so that negative 1 gets multiplied by the negative 2/3. The argument x plus 1 never changes. And the power rule dictates that we change that by dropping it by 1. So 2/3 minus 1 is negative 1/3. Don't forget the chain rule. Actually, if you forget the chain rule in this case, it's okay because the chain rule says multiply by 1 in this case. Again, the derivative of the argument is what we need to multiply by. But derivative of x plus 1 is simply 1. At any rate, this is the same thing as negative 2 over 3 times the cube root of x plus 1. That is the derivative. That is g prime of x. Now, if we try to evaluate the derivative at this point, when x equals negative 1, we need to evaluate g prime of negative 1. And when we try to do that, we find that we're going to take the cube root of negative 1 plus 1. Negative 1 plus 1 is 0. We can do that, we can get 0, and that's going to give us negative 2 divided by 3 times 0, which is 0. Oh, wait a second, that's undefined. That's exactly what we would expect based on the graph. So there's no surprise there. So we've got two different scenarios where we have an extremum, either a minimum in that first example or a maximum in this second example. And in one example, our extremum has a derivative value of 0, and then in the second example, our extremum has a derivative value of undefined. So perhaps you could come up with a conclusion there. If a continuous function has a relative extremum at x equals c, then blank. So pause the video, think about it on your own, see if you can figure out what should go in this blank, and then see if you're right. Well, if our last two examples were any indication, then we have two possible scenarios. Either we have f prime of c equals 0, or f prime of c is undefined. One of those two things seems to be true no matter what. So now we're going to have a definition of a critical number. A critical number of a graph is a value c such that f prime of c is either equal to 0 or is undefined. That's what f is not differentiable at c means. Remember that differentiable means derivative exists. So if f is not differentiable at c, we can think of that as f prime of c equaling undefined. That sure does look like the two possible scenarios here. So if a continuous function has a relative extremum at x equals c, then one of these two things must be true. Well, then we can reword that observation. Instead of saying either this thing or that thing, we could just say, then c is a, you guessed it, critical number of f. Every single time.